And I'm not trying to solve this category theory per se.
Okay, so to start off this morning, we're very happy to have Tull from Continuum talking about causal models and string diagrams.
All right, thanks very much. Oh, it's a bit of a delay on it. Okay, yeah, thanks everyone. Thanks a lot to the organizers for this great chance to speak to you all. It's been a really great conference so far. And it's especially good to be at ACT talking about this causal model work, because as we'll see, a lot of what this talk's about is about taking lots of developments that have been going on in causality in the ACT community, and then trying to get them in a form where maybe they can start being picked up even more by actual causal model practitioners who don't always have a background in category theory. And everything I'll talk about today is joint work with Robin Lorenz, who's our sort of in-house causality expert here at Continuum. So there's lots of reasons why we might care about causal reasoning, and the precise motivation won't really matter for this talk. So we could be thinking about causal models in terms of sort of hard science models of the world or something, or they could be thought of as, it can also be used in all sorts of areas like policy making, where you're trying to decide how to affect the change you want in the world through some intervention. For us, our own motivation is actually coming from AI. There's quite a big area in causal AI at the moment, which is arguing that machine learning could benefit from, above learning just the statistical models that it normally uses, actually learning causal models. Whatever your motivation is, though, what's nice is that you can sort of formalize causal reasoning very nicely in this framework. It's often just called the framework of causal models, developed by various people, perhaps most famously by Judea Pearl, whose book we see here. And one of these causal models is normally given by the data of a directed acyclic graph, which represents causal relationships between variables, and then a probability distribution, which is compatible with this causal structure. But sort of recently, there's been lots going on in ACT, and we've heard a lot about it this week already, about how we can describe probability theory and causal models as well very nicely in terms of string diagrams. And this essentially lets us work with both aspects of this causal model in one formalism, which I think is what makes actually the string diagrammatic approach really natural for describing causal models. And so you might wonder whether we can kind of capture everything that people normally do with causal models, or the sort of standard core of the causal model framework entirely in terms of string diagrams, and that's what this is heading towards. So as I mentioned, there's loads of prior stuff to do with categorical probability and causality that we're building on here. Certainly not the first to think about these things. So here's just some of the past work I mentioned, but apologies to anyone I've left out. So there's this paper from Bob Kirker and Rob Speckens a while ago looking at Bayesian inference in dagger compact categories, talking about Bayesian inversion and so on. And then maybe a bit more well-known is this paper from Kenta Cho and Bart Jacobs that also looks at Bayesian inference in terms of CD categories, which is the framework we'll be using today, and we've heard loads about this week. And then, of course, there's Tobias's classic Markov categories paper, where a lot of this was extended. In terms of causal models specifically, to my knowledge, the sort of early start for this is Brendan Fong's master's thesis, where he looks at Bayesian networks from a categorical perspective. And then my own sort of introduction to causal models, and I think our starting point for how we treat them here, is this paper by Jacobs, Alex Kessinger, and Fabio Zanazzi, called Causal Inference by String Diagram Surgery, which has the kind of which features the kind of diagrams we'll be using today. And there's been more going on since then, though. In particular, there's this paper from Tobias Fritz and Andreas Klingler, which is also looking at aspects of causal modeling and sort of generalizing causal models in Markov categories. So we've seen there's lots of these different developments going on, and we might wonder if we can kind of package them together and fill in some gaps to be able to present sort of the standard core of the causal model framework entirely in terms of string diagrams, to have something kind of comprehensive. That's kind of what we were aiming for in this paper, Causal Models and String Diagrams. It's rather long. And I'll try and give a sort of overview of what's in there today. So this could be motivated by either, as I said, sort of being able to show causal model practitioners who don't normally know about string diagrams that they can be useful by letting them see how to treat the things they like to do with those. Conversely, if you don't know causal models but you know string diagrams, it's sort of an introduction to these parts of the causal model framework. And one way to sort of capture what I mean by capturing like a big core of this causal model framework is to say we're going to cover all the different levels of what's called Pearl's hierarchy. I'll kind of use that to guide us through the talk. So Pearl's hierarchy is this hierarchy of different kinds of model you could have. At the bottom rung is sort of just plain statistical models that let you just answer associational questions about your data. A rung up from that, we have actual causal models themselves, and these let us answer interventional questions about the data, which are what happens if we change things. And above those is actually a sort of more refined notion of causal model called a structural or functional causal model, which let us address things called counterfactuals. So we'll talk about all these kinds of causal model and these notions of interventions and counterfactuals today. To get started then, we'll just start at the bottom rung, which is just plain statistics. So basically this is just our background setup, and that's categorical probability, which we've heard loads about this week already, which is really useful. So we're always going to be working in a CD category. We've seen this loads of times now. So we're in a symmetric monoidal category where every object has this chosen copying map and a discarding map. And these form a commutative comonoid, and also the choice of these is natural and so on. And I'm reading all my string diagrams from bottom to top here. Actually, for this talk, you only need one example of a CD category for all our illustrations. So that's this category I'll call MATR+. So here the objects would be finite sets, and a morphism from X to Y, drawn as this string diagram in the bottom left, would be a matrix where you think of each X as an input and each Y as an output, and for each one of those you have a value M of Y given X that's a positive real number. If we plug these together in sequence, this just corresponds to, yeah, you can see the mouse. This corresponds to summing over the internal wires. So this is like matrix multiplication, and in having them in parallel, it's like taking the tensor of the matrices or just the Cartesian product of the sets. So we're thinking of one of these boxes as a kind of probabilistic process, but at the moment there's no requirement that it's normalized in any way. So it's just giving each Y value a positive real number for each input. Useful to be able to talk about the actual fully probabilistic ones in there, which here we call channels, but sometimes they're called total maps, as we've seen. So these are the ones that preserve discarding, and that means the matrix is stochastic. So it actually sends each X to a normalized probability distribution on the other side. So in particular, states normalized. When you discard it, you just get the unit on the monoidal unit, sorry, the identity on the monoidal unit, and that means it's a probability distribution. And as we've probably seen already a lot, we can use discarding to marginalize things, and that just corresponds to marginalization in the normal probabilistic sense. So I will need a bit more probability later, but I think it's more interesting to head up now to our view of what causal models actually are. So the standard view for what a causal model is with what's called a causal Bayesian network. So we have a load of variables, this x1, x2 up to xn, and we want to reason about these causally. So a causal model for these variables would be given by usually these two things, as I've mentioned, a directed acyclic graph, where the vertices are the variables, and in this view, a load of probability channels where you specify each variable in terms of its parents in the DAG, which means the things that have an arrow going into that variable. So here we have an example of a causal model describing possible causes for lung cancer. So we have a variable L for whether or not you have lung cancer, S for whether or not you smoke, A at the bottom for the age of a participant, and B for some relevant background conditions that we could be reasoning about that might determine whether somebody smokes, but also might be a common cause as to whether they had lung cancer. So, yeah.
So that B is not circled, or?
Oh no, we'll get to that. Yeah, yeah. Thanks. It does mean something. I'll just tell you now. Yeah, the fact it's not circled means it's a hidden variable here, and so the AS now would be observed. Now I'll get to that in a second. Yeah. So for each one of these, yeah, so just to read the DAG, obviously what it's saying is, for example, lung cancer could be caused by any of the other variables because there's arrows coming in from all of them. Whether they smoke is just supposed to be caused by these background conditions. And the background conditions are just meant to be caused by their age, and the age isn't caused by anything here. So for each one of these variables, you'd give a probability channel, like on the right. So for lung cancer, we'd have to have all the other variables as an input. For smoking, it would just have these background conditions. And age doesn't have any parents, so the channel would just mean a distribution over ages. And then you can multiply these things together to obtain a distribution over all of the variables. And yeah, the other ingredient that David pointed out is that often we only have a subset of these things that we can actually observe, and the rest are often called hidden. So here I've circled the observed things. So you're normally starting from the distribution on these observed ones. So for example, we'd have a distribution just correlating age, smoking, and lung cancer. And then we want to postulate different possible causal explanations for this distribution. So that would be talking about different DAGs that could relate to variables, and also different possible hidden variables that might appear as well, such as this B here. So that's basically the standard picture of causal models, and we'd like to now put this into a general CD category. Because of the way we framed it here, this is basically immediate, right? We just have to replace these probability channels with channels in our slightly broader sense. The definition we can give of a causal model, M, in a CD category C, is that we give one of these DAGs with vertices, and I'll normally slip between calling them vertices or variables, probably normally variables. A subset of them that we consider to be observed, or that we call outputs, and for each one of these, an associated object that we just denote with exactly the same letter. So for each vertex, we'd have this object xi as well, and a channel that produces it in terms of its parents from the DAG. So this is a tensor product in our CD category over the parents, Ci, and we call this channel a mechanism that produces that variable. So yeah.
All the mechanisms have to be one output?
Yeah, that's right, yeah. Thanks for pointing that out, yeah. So the data is just to give a one output mechanism for each variable in terms of its parents. So those are the only kind of channels here, basically. So if we take this definition in our example category, we get causal Bayesian networks in the sense of the previous slide. So that's all perfectly fine. It's not fully, we might think of this as not being fully string diagrammatic yet, though, because we've had to still talk about a DAG and then some extra morphisms floating around here, right? So we'd like this to be fully in string diagram form. There is a nice known way to do that. Goes back to sort of implicitly in Brendan's thesis, I'd say, and in the Jakobs-Christian-Zanazi paper. So basically, there's a correspondence between these DAGs and a certain class of string diagrams that we call network diagrams. And we're best just shown with examples, but then they're diagrams built from these components. We can have copying morphisms, we can have boxes with just a single output, and we can have discarding maps in there. Well, most of the time you don't need to draw any discarding maps. And the result is that for any DAG, you can draw an equivalent one of these network diagrams, where the labels in the boxes are kind of arbitrary. But what you do is, for each variable in your DAG, you have a box with that as the output, so you have a wire labeled by that variable. And the inputs would be its parents from the DAG. And then what you do is you copy each variable and pass it to all of its children, and also you copy it out of the diagram an extra time if it's an output. So this lets you already see just from the diagram which variables are the observed or the output ones and which are hidden. In this example here, x2 has x1 and x4 as its parents, so it has wires coming in from those, and it's an output, so it gets copied out as well. So we basically equivalently turn the DAG into a string diagram, fine, but the point is that now we can say what a causal model is by just interpreting this string diagram. So to specify a causal model now just amounts to drawing one of these network diagrams and specifying what all the actual objects, so we pick a CD category you want to interpret in, and then we just need to pick actual objects for the wires, actual channels for all the boxes. So another way of saying what a causal model M in a CD category is just to say that it's an abstract network diagram, so it's just a syntax, with no inputs in the diagram, I should say. And then an interpretation of the diagram, which means choosing objects for the wires and choosing channels for all the boxes. So our smoking causal model example would now look like a network diagram like this. This diagram is equivalent to the DAG we drew before, and we just say it's this diagram in the CD category, meaning it comes with the interpretation in there so that there's actual objects for the wires and actual channels for the boxes. Maybe here we all like categories, but a lot of other people will probably ask, why would you do this over the standard definition of causal models? So as I've alluded to, I'd say the strength of this over the previous view is that normally you have to keep switching between working with a DAG and these probability distributions or probability channels, so you're jumping between the sort of graph theory aspects and the probability calculations. But as we all know now, you can do a lot of probability theory just with the string diagram, so you can basically describe the model, so you get the benefit of the graphical depiction of the causal structure and reason about it in one setting. It also lets you start to generalize things. So here I had to say network diagram with no inputs on both of the slides, but there's no particular reason to enforce this, especially once we're thinking compositionally. So what if we just drop this no inputs idea? We can then obtain a notion of causal model with inputs that we'll call an open causal model. So formally, these correspond to a slight generalization of DAGs that we call an open DAG. So an open DAG is just given by a finite DAG, now with a subset of outputs like we had before, and also a subset of inputs now is the new thing. And the only condition is just that the inputs can't have any parents in the DAG. So we can draw an open DAG like this, where we we've just circled the outputs like before, and they can be anything. You can just circle any variable as an output. And if it's not, you'd think of it as a hidden variable. And for the inputs, we have this notation here where we're just drawing some incoming arrows going into them. And they just have to have the property that there's no parents for them already in the DAG. So then we can define this open causal model idea. So basically, it's just the same definition as before. So you give an open DAG, and you give an object for each variable, or each vertex in the DAG, and you give a channel. And the only difference now is you give channels only for the non-inputs. So the ones that are inputs are supposed to not actually have a specified mechanism. They're just inputs to the whole model. But all of the variables that aren't inputs have mechanisms. Probably the simpler way to view it, though, is just to say it's a network diagram now where it can have inputs with an interpretation in terms of objects and channels in your CD category. So this is a general network diagram now that corresponds to the open DAG from the previous slide. So we've got x2 and x3, the inputs here now don't have mechanisms, they're just coming into the diagram. The other variables do have mechanisms because they're not inputs, and they behave like before. And again, we copy the variable out if it's an output. And yeah, for those who want to ask about it, these are, those who know about Fritz and Klingler's generalized causal models, these are basically a strict subset of those, and we can talk about it at the end perhaps if people are interested. So what's nice about these open ones, as you might expect, is that we can compose them. So open DAGs you can plug together. And I think the composition on those is essentially a special case of the composition of open graphs that's been studied by John Byers and Brendan Fong and collaborators. So you can plug these up and you just kind of identify the selected inputs. Yeah, it does work in this example. So you're identifying the outputs from the first one of the inputs of the next, obviously. It's probably more natural, even easier to think about this composition when you're just looking at the diagrammatic level here, though. So you can plug these open causal models together, and it just amounts to, well, I'll just say that means they form a symmetric model category. So in any CD category, we can build this symmetric model category OCM of C for open causal models in C. So we can have morphisms now. We can draw an open causal model like this, where its inputs, this bold X is meant to be a list of objects, an indexed set of inputs objects from C, and similarly for Y. And there could be further variables inside the box, as it were. So this is an open causal model with inputs X, outputs Y, and maybe some other stuff going on inside. And when we plug them in sequence, it just amounts to drawing the diagrams on the page on top of each other and just inheriting the interpretations from the two models we already have. And in parallel, it's obviously even simpler, you just draw them alongside each other. So now I've talked about how we view causal models. I'll move on to what we actually do with them. So the main thing is that they let you answer these so-called interventional questions about your data. So what we want to do now is talk about interventions. So yeah, causal models that you determine what happened if you were to change things. So you don't just have the correlations between your variables. You can
I was just wondering, you allowed for discards in your causal models, right? But I don't think you've used any yet.
Yeah, that's true. Actually, I don't think they're shown in the. So yeah, it's a good. We could have a network diagram where we had a mechanism and then it was just discarded, and maybe that might seem a bit unnatural. We've allowed it in our setup, so it would be like the variable's there even though it doesn't get passed anywhere and it's not observed. But I think it can be useful to formally allow for that case. But that's slightly different too. Maybe that slightly breaks this idea that these are a strict subset of the Fritz and Klingler's models. Yeah. Thanks for that. Yeah. So an intervention in general is just supposed to be a reaching in to change the underlying causal mechanism. So we just define intervention in a very broad way as just any modification of the mechanisms of a model. It could be an open model. So you keep the variables the same, but you're allowed to change the mechanisms however you like, and the only requirement is that you would have to still end up with something that would be acyclic at the end, so it would have to correspond to an actual network diagram. And now I'll just talk about lots of different examples of these. So in the literature, when people say intervention, most of the time they mean what's called a do intervention. So this is where a do intervention for this variable xi would be where you look at the mechanism for that variable, and you simply throw it away, and then you plug in a sharp state for xi instead. And by sharp, I mean deterministic in the sense of CD categories. So we often call them sharp, that's the same thing. So a state which is copied by the copy map. When you're in MATLAB+, as we've heard this week, these sharp states correspond to point distributions at x, so they're basically elements, and this is just saying, ignore whatever the normal causal mechanism is for that variable, just fix it to this value x. So for an example, when you do these interventions, it amounts to doing this kind of surgery on the string diagrams. So a do intervention here, let's imagine this in our smoking example. So we say we want to intervene and force everyone to either smoke or force them to not smoke, which might be wiser, is that you select the mechanism for smoking, S here, and you do this do intervention. So you would just throw it away and replace it with this sharp state S that's say yes or no. And then you can go on to reason about how that affects the distribution. So if you take the diagram and just interpret it now as a distribution, as a state in your CD category, you've got a new distribution. And you can imagine that in other cases there's more interesting calculation to do with the effect there. So the diagrammatic approach kind of makes it easier to talk about much more general kinds of intervention. So they are sometimes considered in the literature, but they're not as commonly. But an example of this is what we call a breaking intervention. So there's no reason why we had to do a sharp state before, so we could just replace the mechanism with any distribution. A very natural kind as well that we talk about is this, what we call a local intervention. So that's where you take the mechanism that's normally there for your variable, and you just kind of do some post-processing afterwards. So you imagine that whatever would normally produce your variable in the world still happens, but there's some agent, say, that has access to it and does this extra process eta that would be another channel living on top here. So for an example of, you can imagine that this also potentially brings in some extra causes as well. So it can alter the DAG in that way. So it would have to be the case that these variables A that you bring in don't now make the thing no longer acyclic, so it does have to remain acyclic. So just an example of those. Let's say we implement a slightly more plausible policy where we just say make smoking illegal for those under 21, so this puts off 90% of those people from doing it. So this would amount to altering the mechanism again for S in our causal model. Now what we would do is we can imagine that, say, the usual process CS occurs that would determine whether somebody would smoke. That's still the case, but now this extra thing is happening that's making 90% of them stop. So that's this extra channel eta S that brings in age as an extra factor. So the age wire you can see is now running up. So now in the new network diagram, where we collapse those into one mechanism now, what's in the blue box, we would now have that A is a cause for S. You can do loads more of these kinds of things, obviously, so we could keep going. From the diagrammatic perspective, there's some that you might not, a bit more natural you might not think of. Normally would be things where you're kind of playing with the diagram, like these ones we called rewiring interventions. If you had two variables that had the same underlying object, you can imagine kind of swapping their mechanisms around, and you can imagine playing around in all sorts of ways with these diagrams. More generally still, oh, sorry. Yeah. The inputs and outputs, you mean? Yes, they would do, yeah, I think. Ooh.
You mean the global boundary?
No, the first one you showed.
Yeah. Which one?
My question was the same. Like,
Sorry?
you're allowed to change the parent set.
Yeah.
That seems weird. Yeah. Are there any constraints on that?
Yeah. Sorry, I've tried to say there's constraints that you couldn't change the parents arbitrarily because you might not end up with a DAG anymore. If you made one thing the parent of the other and the other the parent of that, it would be cyclic now. So there are constraints on.
Just replacing any other morphism with the same code.
Yeah. It's not like a particularly restrictive definition, right? So we just anything like that we call an intervention, and then you would expect to study these sort of restricted families of these things, like do interventions and so on. Sorry, did your question get answered, do you think? It might be sort of addressed here where a bit more generally than interventions now, we just like to talk about transformations of models. So this is even looser thing now where it's just a way that we refer to the idea of building new open causal models from old ones, basically. So an open causal model, a transformation of a model now just refers to any modification of the mechanisms, and you can also modify the variables now. So it's just used just as a way of talking about building models from old one, but it doesn't really restrict you in any way. The one that's quite natural is what we call opening, which is where you take a causal model you've already got, but you turn some of the variables into inputs now that weren't previously. So this is changing the inputs and outputs of the model as a whole. So we've got a subset of the variables S. We can just imagine opening it there to make those inputs. And that would just amount to throwing away the mechanisms for that variable. And the reason that it could be natural to talk about this is that you can think of a do intervention in terms of this transformation. So doing a do intervention at S, like I said, just amounts to throwing away the mechanism for S. So you could also view that as taking a model, opening it at S, so you're just getting rid of the mechanism, and then composing it with this value you want to do the do intervention of. But now that composition on the right is something living in this category of open causal models, effectively. Yeah, at the level of the diagram, it would just look like we'd expect. So on the left, we have our model, and opening at S means getting rid of the mechanism for S, so it just passes in as an input now to all of its children in the DAG. And if you interpret that whole channel on the right, it would, in the sort of conventional literature, you'd write it something like this: P of SL on A given your do intervention on S. So, and that's because, you know, if you plug in any sharp state as the input, it would correspond to that do intervention that we saw earlier. Okay, yeah, really briefly, I just mentioned some other ones. So because transformation is so general, you can just do stuff like changing which variables are inputs and outputs, which we talk about as well. So if you make some variables no longer outputs, so you're basically turning them into hidden variables, that actually corresponds to marginalization in this category of open causal models. So that's this internalizing, this int A at the top. Conversely, you could imagine the notation at the bottom is just informal, but that's the idea of taking some variables and making them observed now. It's a sort of reaching in to your morphism. And I just mentioned this because, you know, the fact that you can do this to me means that this OCM of C is obviously more than just a symmetric monodal category. It has this kind of feature that there's this reaching in ability for certain morphisms, but I don't really know how to capture what that is formally yet, so I'd be curious if anybody has thoughts about that. Okay, so returning to the hierarchy now, so we talked quite a bit about causal models and these interventions and more general transformations. So the next level up that I mentioned is that there's this kind of more refined notion called a functional causal model. So we'll see how we depict those, and then eventually get to these counterfactuals. So the idea is, let's say we start from our variables, x1 up to xn again, and in a functional causal model, we basically want to give functional mechanisms for those variables now. So to do so, they're called the endogenous variables. You introduce these extra set of variables called the exogenous variables. I'll probably just call them background variables most of the time. So for each one of your original variables, x1 up to xn, you have this now new background variable, u1 up to un, so they pair off like that. And the idea now is that the model looks like this. So the background variables, ui, has no parents, so it just has this distribution, the lambda I here, as its mechanism. And now the variable xi has this functional mechanism where it just has some subset of your original variables here, these endogenous ones, and then this background condition. So its mechanism is this box fi. And by functional, we can generalize to meaning it's a deterministic morphism in our CD category. And it would be a channel as well, sorry, so a deterministic channel. So the main example, of course, in MATR Plus, these deterministic things really do correspond to functions, and these models are normally called structural causal models, but sometimes functional ones as well. And the idea is that causal mechanisms that exist sort of in nature out in the world should really be functional, and it's just our ignorance about the underlying, like all the relevant background conditions that makes us have to have these channels in our causal model. So in a functional causal model, you imagine you've separated those out, this variable ui, and you've kind of got to the real functional causal mechanism that's going on underneath. Particularly, you can imagine going from a regular causal model, like our smoking example, and kind of refining it to this functional causal model where you've introduced these background variables for each variable that you had originally, and now you have a functional mechanism, so a deterministic one. And this is certainly non-unique, so there's loads of different ways that you could decompose your channels into this choice of a function and a distribution. Yeah, this is some stuff that I could have put at the categorical probability part at the beginning, but I just thought we should get into causal models. So to treat counterfactuals, we need an approach to conditioning. Obviously, it's very similar to what was in Elena's talk on partial Markov categories, but it's a slightly different approach, I'd say. Yeah, so let's get into it. So we want to talk about conditionals in the CD categories, and particularly want to kind of talk about a distinguished chosen conditional for our approach. So the way we do this is via a notion of normalization. So in general, what we in the paper, we give the idea of a CD category with normalization, meaning with chosen normalizations. So that means for every morphism F, there's this chosen morphism that we depict with the blue dash box around it here, called the normalization of F. And it satisfies this condition, which I think is the same as from Elena's talk, for being a normalization of F there. But here it's a distinguished one. And it satisfies, this mapping satisfies the graphical conditions. So in particular, each one of these normalizations is a partial channel, which basically corresponds to the quasi-total idea from the partial Markov categories work. And there's sort of axioms, for example, the normalization is idempotent, so each thing is its own normalization, and these normalizations factor through copying and discarding and so on. So we're going to use these to define conditionals eventually, and then we'll see what the main example is when we get there. The only other thing we use is having caps in our CD category now, so this is restricting things somewhat more. So that means each object comes with this distinguished cap that lets us bend outputs into inputs that's compatible with the copying structure. And for these to be really useful here, we need this condition which does kind of restrict us to a fairly discrete kind of setting, I'd say, which is that if you compose two morphisms with the cap, you get the same thing, and the two morphisms to begin with were the same, which does hold in MATLAB+, but it's not going to work, I think, in really general measure theory settings. And so then, we can take states such as sharp states and turn them into these effects by bending them around. So once we've got all this together, we define a sort of chosen conditional for each morphism as the following partial channel. So if you have F from X to Y, X is the input and Y and Z is the output, so you can do the conditional by Z by taking F, composing with this cap to turn Z into an input, and then you need to normalize the whole thing to turn it into a partial channel. And in MATLAB+, this corresponds to what I think we call the minimal conditional, the sort of canonical one from the talk. Yeah, and so it's one where it's when there's an obvious choice for what the conditional should be, it gives you the usual notion of probabilistic conditional, and when it wouldn't be defined, so you would normally be free to specify it, however, it's just set to 0, so that's why it's a partial channel and not a channel. So if you have some X and Z where there's no Y's that would ever happen according to your channel, then you just set the whole conditional to 0 on those. And so, yeah, so it basically corresponds to the conventional way you'd write conditionals in a probability theory notation, and in particular, we can do stuff like pass the sharp states inside in these pictures. Okay, so all of that was just because conditioning is going to come up when we talk about counterfactuals now, and these are like a more refined kind of question than these interventions. So here's an example of a counterfactual question. So let's say Mary wakes up with a headache, and she wonders, or we wonder, had Mary taken an aspirin last night, or she's still woken up with a headache today? So this is a counterfactual question. We can't answer it directly because we'd have to go back in time, as it were, and deal with this exact same Mary. But if you have a functional causal model, you can give a meaningful answer to these counterfactual questions. So let's imagine we have a functional causal model for this situation. So there's two variables, A for whether she takes an aspirin, H for whether she gets a headache, and they're just yes, no valued. And we have functional, so we have these background variables, UA and UH for each with some distribution over them, and we have these functional mechanisms. So F would determine whether or not she takes an aspirin in terms of these background conditions, and G will be a function determining based on that and the other background conditions for H, whether she then goes on to get a headache. So if you want to answer this counterfactual question, it basically amounts to commuting this distribution here, which I'll walk through now. And you can think of it in terms of considering two different hypothetical worlds. So at the bottom, we have the background conditions that we've pulled down, so the background conditions for each variable. And we're copying them and passing them to each of these two worlds. So on the left, we have a diagram corresponding to the actual world, as it were. So we leave, in the blue, we leave the functional causal model alone. And we just plug in the knowledge that we have about what happened. So we plug in that we know that she didn't take an aspirin and she did get a headache. So we plug in those sharp effects for those. On the right, we consider now an imaginary world where we suppose that she did take an aspirin nonetheless. So that amounts to doing a do intervention on the functional causal model to obtain this, well, on the functional part of the causal model, rather. And ending up with this one here instead. So where we just force the aspirin value to take the value yes. And then what we do is do this normalization around the whole thing, so we can view this thing as a conditional to obtain an actual distribution. And this distribution on the right is over, now would give us the probability of whether or not she would have got a headache in this hypothetical world. So yeah, the way to think of it is that we have these background conditions at the bottom that are like what are linking these two worlds. So on the left, we're basically restricting ourselves with these sharp effects from what we know actually happened, which is that there was no aspirin and a headache. So we're restricting the background conditions to just those lambdas and lambda dash that would have led to that happening, but now saying, what if we just forced the aspirin to be taken instead? So it's sort of intuitive that this gives you the right distribution in the end. And you can imagine in doing rewrites and so on to compute this thing. So we use this to give a general definition of counterfactuals. So you start from a functional causal model and you split it out into all these background variables at the bottom, and then a deterministic part. So this diagram would be in the category of open causal models. So all the background, this L is the model, L stands for latent, so it's the latent variables, the background ones. And that model would just be all your priors over those independently. And the F at the top would be just all the deterministic parts from your functional causal model, so all the functions. And then in general, we can say a counterfactual is a state like this, where we have now these k different parallel worlds, as it were. And so the background variables at the bottom, again, being copied and passed to each of them. And with each parallel world, you can do the same kind of thing as in the last example, basically. So you can have do interventions going on changing your functional mechanisms. Because do interventions also sharp states, you still have a functional thing in there after you do one of those interventions. You can also condition on some facts that you know, like when we conditioned on the aspirin being taken or not taken. And then you can basically care about some of the variables, so you pass them out, and you probably don't care about some others, so you discard them. And this overall would sort of encode an answer to a counterfactual type statement. And generally, the counterfactuals, the way they're talked about in the literature, can be a little bit muddled. So we hope that this kind of categorical formalization kind of helps clarify the distinctions. Okay, so what we've done now is work our way up the hierarchy. And there's one part of the paper I'll talk about if I have time. So we've seen how to treat all of these aspects. Final thing I mentioned is something similar to in Isaac's talk. We're talking about identifiability. So we talk a bit about that in the paper too. So the idea of identifiability is, if we have a full causal model, let's just think about interventions, say, it tells you what would happen under certain interventions. So you can calculate things like P of Y given Z, so some conditional, and given some do intervention X. And you might be able to calculate, so if Y, Z, and X were part of your observed variables, you could compute this thing. But often you don't have the whole causal model, you just have some sort of partial causal knowledge. And these often formalize with what are called, not DAGs now, but these acyclic directed mixed graphs, which are like DAGs, but you can now have these bidirected edges in the picture as well. So here we have a bidirected edge from X to Z. So given this sort of partial causal knowledge, we wonder if we can still answer these questions. So what you do is basically go from one of these ADMGs and turn it into a DAG. And there's a couple of different ways you can do this, but they'll all end up giving you the same answer to these questions, so that's nice. And we call this routification. So in this case, we're just introducing a extra variable for each of these bidirected edges. So this variable r has been introduced to capture this potential correlation between x and z here, or potential common cause rather. Okay, and then once you've done this routification, this is equivalent to a DAG or a network diagram. You can go on to do the reasoning about the interventions that you want to know, and then you can determine whether or not one of these things is identifiable by doing some rewrites on your diagrams. So let's say we're thinking about this kind of thing, like we had p of yz given do x. If this is your causal model now, we can just use the stuff we talked about earlier to write down the corresponding channel. So we're opening x here and doing some rewrites. We can so we rewrite it to this form just by pulling some discards through. And now let's say that we care about conditioning on some specific z in our example. So we're looking at p of y given some fixed z value and a general do intervention. So you would do this conditioning that we talked about and this normalization here. So in this case, it wouldn't be identifiable. And the problem is that we've got this CR here, and this R was one of these root variables we introduced. So it wasn't there in our original model. It was just something we kind of added in from our ADMG. So there's no way we're going to obtain this distribution over this hidden variable R just from our distribution over the observed variables. So in particular, that means that this thing won't be fixed. So this is called not identifiable. But conversely, if we just were thinking now of the marginal of the kind of stuff we were looking at before, so we marginalize over z, we just look at p of y given do of x. We can pull the discard through. We end up with this thing. So this is just looking at the marginal on y basically, and we just discard x here. So this is something where the components of the diagram are all just determined by distribution over the observed variables. So in this case, this would be identifiable. So there's generally a question for each kind of possible partial causal structure and each kind of intervention, whether it's identifiable or not. So in the paper, we just do lots of examples for this and try to show that the diagrams help you think about these things. But there's no sort of complete algorithms for reasoning about identifiability in the causal model literature. So in future, it'd be kind of nice to give a full diagrammatic view of those algorithms and see if the string diagrammatic approach helps with those things. And we kind of made a start on that for counterfactuals. I'll just really briefly mention this just to show that we have kind of algorithms in the paper. This first one allows you to simplify the sort of diagrams that appear in these counterfactuals I'd showed. And then you can go on to talk about whether a given counterfactual is identifiable or not in just kind of the same way as I was talking about for interventions. So this algorithm Robin found is basically a diagrammatic translation of an existing algorithm, I believe, in the causal model literature. And I think there's, because it essentially corresponds to that, it should be complete, but there's not a full formal proof yet. Okay, I've talked about a lot of stuff, so I'll try and wrap up now. The main takeaway is supposed to be and I'm preaching to the choir here, so it's not going to be very controversial, but the string diagrams are good and that they're the natural home for talking about causal models. In particular, we saw how to draw diagrams for these various aspects of causal models and these new open models and interventions and counterfactuals and so on. There's lots more stuff you could do with this, obviously, so we could keep going trying to absorb more known existing aspects of the causal model literature into this perspective. A bit more interestingly, so the approach to conditioning I used was, I kind of mentioned that it's fairly discrete in the way it works. We use these actual presence of these cancellative caps in our CD category, which works for MADR+, but it doesn't work in general. We've had lots of discussion about conditioning already here at the conference, but yeah, it'd be nice to, I think that for treating the continuous settings, we still have an intuition that you would like a kind of chosen conditional, because you really want to talk about a specific thing when you're talking about identifiability questions and so on. And so we're looking for a notion of a sort of chosen conditional, but in a more general CD category. The kind of bigger questions that we're personally interested in this work at Continuum are to do with relating causal models to AI and this notion of compositional or kind of category-theoretic intelligence that I briefly, that's like our motivation for the work. And if you care about causal models in machine learning, I think that one of the big problems is what's called causal representation learning. So this is about, if you're just going from raw data that you're training from, how is the system supposed to actually learn what these causal variables are? So how do you go from just raw data to a causal model? That's a very hard problem that's a big question in causal machine learning. Finally, another big direction is to look at quantum versions of this. So we're in Continuum, we care about quantum stuff too, or primarily in fact. And there is a notion of quantum causal model, corresponding to sort of an analog of causal model. So rather than giving the internal structure of a distribution, as we had with our kind of network diagram here, in these quantum causal models, you often have the internal structure instead of a unitary, which is talking about the causal relations between the inputs and outputs. And there's various conjectures about how to go from the relation to the inputs and outputs of a unitary and a corresponding kind of string diagram. But some of these are very open, and this is what Robin's been working on. But for now, yeah, I'll stop there. So thanks very much.
Thanks, Sean, for the very clear and interesting talk. So we've got plenty of time for questions. Yeah.
Yeah, can I ask a question online?
1 second, we've got an in-person one first.
Okay.
Thanks for the talk. So I really like the counterfactuals with string diagrams. I think that's very cool. And I have many questions on that, but maybe you can pick what you have thought about. So for the counterfactuals, you had these functional causal models. Could you express counterfactuals also for non-functional causal models, or maybe for like a part of the causal model rather than the whole one? Like, let's say you want to only consider counterfactual for like a subpart, a small part of the whole causal model. Is that possible? And in particular, I think what's very interesting is counterfactuals for quantum causal models, if you have any thoughts on that.
Yeah, thanks a lot. So yeah, I think it can be quite sort of, there's a lot of debates in the causal model literature about being really precise about defining these things. So you sometimes have to be quite careful about whether counterfactual would always make good sense when it's not functional. But we do talk about, so quantum counterfactuals definitely is very interesting. And part of the motivation of just even doing this for us was to get the classical causal model stuff really just ironed out. Like, it was clear it could be done, but we just wanted to iron it out and make it clear what it all is so that you can then do quantum generalizations of these things with a sort of clear correspondence. So I don't have a good answer for quantum counterfactuals yet, but I agree it's very interesting. For the counterfactuals with non-deterministic stuff, I think, yeah, I agree there's lots to work out there, and the diagrammatic view definitely helps you very easily start talking about these things and reasoning about them. In the paper, we just talk about the idea of counterfactuals. At the end, we allude to the idea of counterfactuals where you are not just conditioning on sharp facts like aspirin taken definitely or whatever. Like, you could condition on sort of soft effects as well in your category. And then you're basically doing this kind of updating stuff, like in the partial Markov categories talk. So there's multiple ways you can do this when things are soft now. So there's sort of Pearl and Jeffrey style view of what one of these soft counterfactuals to be. But I think the question of also making the functional part soft or whatever is a very good one as well. I think broadly you wouldn't expect there to be no restrictions, because then you could just define counterfactuals with plain causal models and you wouldn't need the functional stuff at all. So there would be some interpretation difficulties, I think, with really soft ones. Thanks.
Any other questions?
Yeah, can I ask a question?
Oh, hi. Yeah, can we have the online question?
Yeah, I do have a question. Yeah, thank you for the talk and very nice paper. And you treat very many different important ingredients of causality using string diagram, but you didn't treat dual calculus. Is there any particular reason for that?
It's a good question. I'm sure Robin will have thought about it a good amount. I don't have a really good answer for that. I don't know if Robin is in the chat on the Zoom call. Might be able to give you something for that one. I think it is a natural thing to think about and translating it into the diagrams. yeah, sorry, I don't have a really. I think it makes sense to include that as well. So I think that you're basically right that that's another missing part.
Okay.
I feel like there is some existing work on looking at do calculus, like Tobias Fritz's will have looked at it, I think. Yeah. Anyway, thank you. I agree, it makes sense.
Okay, yeah, and maybe another question. Is it possible to also include cycles in the causal models via string diagram?
Yeah, that's a good question. I think the view that we've taken here makes it a bit harder to include cycles because, I mean, if we use the definition that sort of started from a DAG, then you can imagine replacing that with a cyclic graph now and still including mechanisms and so on. So you could go from there and start reasoning about cyclic causal models. It would be a bit harder to do it just in terms of a fixed network diagram, other than the sort of thing where you take your cyclic one and you unfurl it, n times, and then you're just running it forward, and now it's something not cyclic anymore. But I mean, there's certainly no like fundamental limitation in treating cyclic causal models categorically in similar ways. I think it's just a network diagram type part that would need tweaking.
Okay, I see. And maybe another question. You only define conditioning for, well, you turn the conditioning on some specific value and somehow turn it to input nodes. And if it's possible to somehow possible to include to input some subsets. For example, we want to condition on some subset. We want some values in some range instead of a fixed value. Is that?
If I understand you properly, I think yeah, you would do that with a kind of soft condition, I think, right? So you could probably that would be nicer done with effects rather than the sort of bending wire approach. But you could have an effect which is sort of like the indicator function for this subset. So you would plug that in to your channel at the top and then normalize that whole diagram if you can visualize that. And that would be like conditioning that your output has to lie within that subset.
Okay, so yes, but if you can turn it input node, then you can change the conditioning, so I think it's a little bit convenient, but yeah.
Okay, so thanks. Maybe we'll take one more in-person question.
So the part where you're rewriting on the string diagrams, there's no requirement that they maintain the boundary. Like can they do arbitrary things to the probabilistic graphical models you started with, the DAG? Like, how do the operations on the string diagram translate back into operations on those DAGs? Because the causal model people really are thinking about the DAGs. Can you think about like retracting them along the?
Yeah, like I was saying, I think so. You're talking about interventions specifically, I guess, right? Or the transformations as well. I mean,
yeah. First, like just from a string diagram back to a DAG.
Yeah.
And then second, when I mutate the DAG or when I mutate the string diagram.
Yeah.
What mutation did I do on the DAG?
Oh, sure. Yeah. I mean, I think it should be so like I was saying, yeah, the way that we define these interventions is so general that you can't say that much, right? Because you're just allowed to do whatever. So you would be studying sort of subfamilies. So there's interventions where you can make clear statements about how it affects the DAG. Like for a do intervention, you can include the thing you did the do intervention on, but effectively you're throwing that variable away. So it's kind of like a transformation. And so you know what you did on the DAG for those, for example. And then more generally, you'd have like interesting classes of interventions and how they affect the DAG. I mean, if you can see, if it's a kind of local thing where you're changing one variable, it's pretty easy to see what you're doing to the DAG. And even more generally, once you plug I mean, if you're doing the intervention, you know how you're plugging the boxes together and sort of collapsing them into one mechanism for each variable. So then you've got a network diagram and it's completely like straightforward to go back to the DAG. So there shouldn't be any sort of problem. There shouldn't be any real differences in talking about how you're changing the DAG or the network diagram structurally. But yeah, I agree. Basically,
it is one-to-one. Like every DAG has a unique string diagram. Every string diagram has a
DAG with chosen outputs and every open DAG. Let's say, yeah, it's one-to-one. But when you're doing an intervention, you might be saying replace this box with this one composed with this. So that's not a network diagram. Now you have to like collapse them into one thing, so that you do a tiny bit of rewriting, say, and then you'd have your DAG. Yeah.
All right, thanks. Let's thank the speaker again.
Thanks.